Hello everyone, I am Nyana Romi, a student from Government College of Engineering, Tirunelveli. Now I am going to present a project on washing machine simulation which I developed as a part of my internship. This project demonstrates how embedded systems can be used to replicate a real-life appliance. This project was completed during my internship at Emertxe Information Technologies, Bangalore. The internship was conducted online between May 13 and June 18, 2025. During this time, I worked as an embedded systems intern where I gained valuable experience in embedded C programming, microcontroller interfacing, and development tools like MP and PiximLab. This internship provided a platform for practical, project based learning guided by industry experts. Through this internship, I developed various technical and soft skills. It followed a project based learning model which encouraged deep hands on learning. The program covered fundamental concepts like variables, arrays, functions, and pointers, and extended to advanced topics such as macros and preprocessor directives. This foundation was essential for effectively programming and simulating embedded systems like the washing machine we will explore now. Embedded C is a programming language used to write application for embedded devices. Unlike general purpose programming, embedded C is designed to communicate directly with hardware components. For this project, I wrote code to control peripherals like LEDs, buzzers, and fans, ensuring the washing machine simulation responded to the user inputs just like a real machine world. At the heart of this project is a microcontroller. A microcontroller is a compact integrated circuit that controls devices. It acts as a brain of the washing machine, processing input signals, making decisions, and controlling outputs. For our simulation, we used PIC16F 8778 microcontroller due to its peripheral support. Next, embedded system. An embedded system is a combination of hardware and software designed to perform a specific function. In our case, it simulates the operations of washing machine. Embedded systems can be categorized as standalone, real-time, networked, or mobile. This simulation falls under the standalone category and it demonstrates how an embedded system can manage multiple hardware interfaces efficiently. The primary goal of this project was to simulate the working of fully automatic washing machine using the PIC16F 877A microcontroller. We aim to understand how to interface different peripherals like switches, LEDs, and fans, and how to write efficient embedded C code to simulate the real machine function using the PiximLab simulator. This project replicates a fully automatic washing machine where users can control washing, rinsing, and spinning cycles through switches. Feedback is provided through a character LCD and buzzer. A fan is used to represent the motor. The simulation closely mimics the real world operation of a washing machine. We use MPLAB X IDE for writing and debugging our embedded C code. PiximLab for used for simulating hardware's behavior without needing actual devices. The microcontroller was PIC16F877E, a powerful 8-bit controller ideal for such projects. Together, these tools created a simulation environment. MPLabX IDE is an integrated development environment. It allows us to write, compile, and debug code specifically for microcontrollers. It supports various compilers, including XE8, which we use to write embedded C for 8-bit controllers. XE8 is the compiler that translates our high-level embedded C code into the machine code executable by the PIC16F877E. It ensures code optimization and compatibility with MPLABX. Using the XE8 compiler was crucial in creating efficient and compact code for the simulation. PiximLab. PiximLab is a powerful simulator that emulates PIC microcontroller development boards. It supports real time testing of embedded applications. This allowed us to test our washing machine simulation thoroughly without using any physical hardware, which was ideal during an online internship. The PIC16F877A is a microcontroller that supports analog to digital converters, timers, and digital input output. It is widely used in industrial applications due to its reliability and built in peripherals. In our project, it served as a center controller managing all operations of the washing simulation. The microcontroller is used in various real world applications such as security systems, remote sensors, home automation, and more. Its flexibility and feature rich architecture make it ideal for embedded system projects like our washing machine simulation. Peripherals like the CLCD, LED, buzzer, fan, switches, timers, and interrupts play a vital role in the washing machine simulation. These components allow us to mimic real washing machine behaviors. For instance, displaying cycle information, alerting users, and managing operations through software. There are five ports in PIC 16F877A. The LEDs are connected to port B and port D. Tris register is used to control the pin direction. In port B, there is one more register called Tris B. Tris register is very important for input output configuration. Since LEDs are external, port direction is driven as output. LEDs LEDs are connected to the output pins of the microcontroller and are used to provide visual indications such as whether the machine is washing, rinsing, or spinning. They are simple, reliable components and are ideal for embedded projects because of their low power usage, fast response time, small size. In the simulation, different LED states correspond to the different phases in washing cycle, helping the user understand the current operation. The digital keypad serves as an input interface for the user. It consists of tactile push button switches, allowing users to control and interact with the machine, such as starting or stopping the wash, selecting programs, or changing water levels. This interface is crucial for embedded systems, where human interaction is limited and must be simple. Since the simulation does not require a large number of inputs, a basic keypad is cost effective and efficient. But there is one problem with this digital keypad. While pressing the switches, bouncing effect arises. Bouncing effect is rapid on-off fluctuations that occur when a switch is pressed or released. It causes error in the microcontroller. To overcome this, we add a short delay to the switches. An interrupt is a mechanism where the microcontroller pauses its current task to handle a more urgent task and then resumes. Interrupts allow the system to react instantly to events like door opening. For example, if the door opens during operation, the system must immediately stop the operation. ISR. ISR stands for Interrupt Service Routine. It is a special function that is triggered when an interrupt occurs. It contains a logic to handle time sensitive events. For example, in the simulation, when the door is opened, the ISR must stop the motor and sound the buzzer. ISR are short and efficient. They don't return values but perform action and return control to the main program. Timers. Timers are essential for managing delays, countdowns, and timing based control in embedded systems. PIC 16F877A includes three timers. They are used here to keep track of washing duration, delay actions, trigger inputs. Timers add precision and automation to the simulation, replacing manual delays and ensuring smooth transition between operations. CLCD. CLCD stands for Character Liquid Crystal Display. It displays the current status or instructions to the user, such as selected program, water level, or error messages. The 16 cross 4 LCD used here supports ASCII characters and works in either 4-bit or 8-bit mode. It uses data and control pin for communication with microcontroller. The CLCD makes the user experience more informative and user friendly in this embedded application. Data storage in microcontroller involves storing temporary and permanent data. The PIC 16F877A includes EEPROM, SRAM, and flash memory. EEPROM, non-volatile memory to store the user preferences. SRAM, temporary storage during program execution. Flash stores the main code. In this project, storage is used to retain selected washing modes, program steps, and timing information temporarily or permanently depending on the function. The functional requirements of this project are: to power on, we use the switch 5. To navigate with the option, we use switch 4. To select the particular washing program or water level, we long press switch 4. To pause or stop the program, we use switch 6. For checking the door status, we use switch 1. These are the inputs to the microcontroller. The outputs are the display. It is to display the washing status in the CLCD. Buzzer for if door is open or else if the washing function has completed. Fan indicates the washing operation is on process. The steps of this washing machine simulation are listed below. Power on screen, washing program selection, water level selection, displaying the function and process, safety checks, program completion message. These requirements ensure the washing machine behaves like a real one and they define how software and hardware components interact. Power on screen. This is the first screen the user sees. After pressing a specific switch, the microcontroller initializes the system and displays the powering on message. After a short delay, it transitions to the program selection screen. This step shows system initialization and user feedback, essential for proper sequencing. Here, the user can select different washing modes such as daily, heavy, woolens, rinse plus dry, etc. using switch 4. A long press selects the desired mode and moves to the water level selection. This screen highlights how multiple user options can be managed using simple input methods in embedded system. This screen allows the user to select water levels such as auto, low, medium, high, max using the switch 4. After choosing the water level, the simulation transitions to the start screen. This simulates real-world washing machine settings, offering flexibility in controlled based on the load size. Start screen. After setting the mode and water level, the screen is where the user starts or cancels the washing cycle. Switch 5 starts the operation, switch 6 and stops and resets the program selection. This slide shows how the embedded system initializes the selected program and passes control to core wash logic. Function screen. Once started, the screen shows the current phase wash, rinse, or spin. The fan starts spinning and the timer counts down. The user can pause or resume the operation using switch 6 or 6.5 respectively. This reflects real time process control, one of the key strengths of the embedded system. This slide ensures user safety. If switch 1 is pressed, the fan stops immediately and the buzzer turns on. The screen displays a warning: door open. Please close the door. Once switch 1 is released, the buzzer stopped. This shows how interrupts and ISRs are used to handle urgent, real world safety issues. When the timer reaches 0, the system stops all operation. The buzzer sounds and the message "Program finished, remove clothes" is shown on display. This indicates that the simulation has successfully executed the washing cycle and is now reset and ready for the next cycle. Now, I will take you through a complete live demo of the washing machine simulation. This demo brings together all the features we have discussed and shows how each function works in real time, as if we are operating a physical washing machine. We begin with the power on process. When the user presses switch 5, the microcontroller initializes the system, displaying a powering on message, and transitions to the program selection screen. This step simulates the real boost up phase of a washing machine, preparing it for user input. Next, we move to the washing program selection screen. Here, multiple modes such as daily, heavy, delicates, rinse plus dry, and many other options are available. Let me scroll through the options. A short press scrolls and a long press selects a desired mode. Let me long press. Next, we move to the washing program selection screen. Here, multiple washing modes such as auto, low, medium, high, max. So, as we seen before, switch 4 is used for scrolling. And let me press long press switch 4. Now we arrive at the start screen. Here we have two options. Press 5 to start the washing cycle. Press switch 6 to cancel and go back to the program selection. Now I'm going to press switch 5. The actual washing process is shown in the function screen. The screen dynamically updates the washing or rinsing or spinning. The fan acts as a simulated motor and the timer countdowns and indicates the remaining cycle time. In here also there are two options, switch 5 and switch 6. Switch 6 to pass. If I press switch 6, the fan stops and the timer also stops. To resume the operation again, we press switch 5. See, the time is decreasing and the fan is rotating. Let's wait until the operation gets completed. Now the washing operation is going on. Now it's rinsing. Next, we simulate a safety mechanism, the door status system. Pressing switch 1 during the cycle simulates the opening door. So let me press switch 1. See, it's showing that the door is open, please close the door. And buzzer also on. Fan stops rotating at that time. Now it's spinning. Let's wait until the time is completed. See, when the operation got completed, it shows program finished, remove clothes, and the buzzer is also on. This marks the end of simulation cycle, resetting the system and preparing it for the next washing operation. Throughout this demonstration, I have shown how each user interaction from mode and water level selection to starting, passing, and safety control is managed through code, timers, interrupts, and peripheral interfaces. The simulation offers a practical, embedded solution that mirrors the functionality of a commercial washing machine using low cost components and educational tools. In conclusion, the washing machine simulation provided practical, hands-on experience in embedded system. It helped understand how software interacts with hardware like timers, interrupts, and peripherals. The project demonstrated how embedded systems are used in automation and control, and it formed a solid foundation for more complex applications in the future. Thank you for your time and attention. I hope this presentation gave you a clear understanding of how embedded systems can be applied to simulate and control real world applications. Thank you.